Hi, my name is Ling Cho, and this is my student number card. My student number is 216542237. Yeah. Right. So in today I'm gonna talk about the my assignment part two, programming assignment part two. Yeah. For the algorithms and data structure subject. So basically uh, we have to implement the word class in here and build a lexicon and export that lexicon into the file. The lexicon is a file where we can find the unique words, the frequency of it, and the neighbor of that one. So you can see in here, word, frequency, neighbor. Neighbor is a list, the list neighbor. Here's the list of neighbor. Neighbor is the list of words. When you can see the function here, the condition for that one, it's the neighbor is two word but only different by one letter. For example, we have uh, bat and cat. It's a neighbor because it's only different B and C letter, right? Yeah. Here, how we rule, how we teach the class, the object, how to return or compare two objects, and here's how we can return that one into the way we want it, the way we can look at it. All right, and the data structure I used in this programming is a hash table. So basically we can see in the construction we have the sign which I choose the prime number because it's going to be efficient, and the reason that I choose that big number because it's obviously the large. There's going to be a lot of word in the input file, so this has to be like much number. It's going to be up to million of words, so the size of the buckets have to be like this. So for the buckets, I create the bucket, and you can see that it's not a normal bucket. It's the buckets inside that element inside that is a list, not only single element. So here you can understand this. It's similar like the buckets into the buckets. Here it's a order method. G function is where we can map the word. For example, by the ASC code. Yeah. After that, we can gain the value from the ASC, the word, and we can, after we map that one, we can use the hash function here to get the unique key for that value element. Alright, so here the function where we can search for that word by using the keyword. If that word exists, it will return the value here, value in the bucket, that one. If not, it return none. Now the insert word is where we can append the word and that keys into the buckets. Alright, the insert mask is the same. I will explain the mask later on, but it looks the same with the insert word. Here it's how you can return all the word in the hash table, which means by later on we will want to return all the words into a lexicon. I also use the quick sort here because the hash table did not have the sort function, so I have to use the quick sort for that. We'll briefly explain the quick sort. The quick sort is use the define and control concept, which use the pivot at the middle of elements, and we try to move all the bigger number of the pivot to the right and the smaller to the left and divide the array again and again and again until it's complete. Here is the build function lexicon called hash table hash table class. Create the object for that, and here read the data. I will use the first read. We will take the whole line of the word from the input file, the whole line token, where I will remove all this non-space, all the and lowercase that one, all the space we remove and lower all the words. And sometimes it's only in the quotes like this, and it's yeah. similar like this. So it have to be, we check if it's not a token, we have to move on, and if that does, we will implant that one into the search in hash table. We will search that one. If that exists, oh, we will compare that one. If it does not exist, we will raise the frequency of that one. If it not, we will insert that words, that token, which is going to be the words, into the hash table. And now it's interesting that I'll make the mask. The mask is, I will create, for example, we have a cat here, so it will repeat, it will have the mask like this, maybe a CT, CET, and CA. So basically, this all three is a mask. The mask is the technique I use for quickly look up for the neighbor that we does not need to like search all the word in the file input or lexicon to match all the neighbor again. I will use the mask technique, so it will create three masks in here. For example, the cat word, and we'll search that word, search that into the hash table. We also hash the mask. If it's similar to the, if it exists, we will append that one into the hash table. So after this one in our hash table, we will have two kind of value and key. The first one is the key value of the word. The second one is the key value of the mask. It's gonna be the mask. Mask gonna be the key when after we hash that one, and the value is gonna be the list of object, list of object word that considered to be the neighbor of that mask. It represent for the neighbor all the different condition for the neighbor. Right. After that, we will sort all that word and use the quick sort later. Get all the word using the, we append all that into the lexicon, and the quick sort will sort all the lexicon here. And here is an interesting one. As I say, we use the mask, right? So we will look through all the lexicon. We generate the mask here, and use the represent for the return value. Use the mask as a key, like I said, as a key to find. We will use the speed of the search in the hash table to find the neighbor, and the mask now. Each mask of a word will contain the list of objects, which means that the list of the neighbor, the same, the word have the same mask with the word we we want to look the neighbor for it. And if it exists, we will append that one with the speed that only on. And if we do not use the mask, we have to use the to for loop to look through all the words in the lexicon and then find the words at the neighbor. It's gonna be long and too extremely large, right? And after all that, we just resort the word and define how we return that one. All right, we'll try to run it and see how it happens. The speed of that. Oh, really quick. I think it's appropriate to 5 seconds. I think we can try this one, so we can take a look at that. How long it would take? I think about 5 seconds. I think. Yeah, 5 seconds. Average 5 seconds. Pretty fast, right? All right, moving on to the next part. It's gonna be a skiplets. The mask and the technique I use in here same. I just change the hash table into the skiplet. So no, so skiplet it's like the multi-level of the linked list, which in each node it contains the pointer point to other table and use a different level. So here we have the key, the value, and the forward. The forward is like I said, to contain the pointer to another node. Alright. Header is something outside to point the first value in the first node in the level. Okay. We will generate level by the random function if it's smaller than p. P is 0.5, which we use that number for the balance in the skip node. We also have the find function here where we can solve for basically it's removed from the biggest level till the lowest number. In here we can see that the forward key um, it will search reverse its line from the large level to the small level, and it's going to be iterate in the left to the right. If that current forward the pointer right to the node that is smaller than the key, it will add the current forward to the current. So basically it's like it will loop until if that number is smaller than the next node in the skiplet, it's gonna be stopped and moved down to level. For example, we have level 3 here. We have 3 to 6. In level 2 we have 1 2 3 1 level 3 level 3 we have 1 to 6. In level 2 we have 1 to 3 and 3 to 6. And level 1 we have 1 2 2 2 3 3 4 5 6. So if we want to find the level 5, for example, it's smaller 1 to 6, right? If we move to down to this one, 1 to 3, 5 is bigger than 3, 3 to 6 it will move to 3, right? And 3 to 6 it will move to 3 to 5, and it will find the find here. And after we find the one, we return the value. Similar to the app entry, it also uses search the similar technique with the finds. And the difference is if it has the current value similar to the key, it will set that into the new value. And if it does not have the node on that, it will generate a new node and level for that. And after doing all that one, it will update the path, the forward pointer for all the nodes and the new node relate to that. Okay, lexicon it's just the way we interface of the skip node, where we can access to all the function in the skiplets. It's a lexicon table here. You can see the insert, find. I don't know. I don't use the deletion here. Here's the returns, similar. And all here is similar to the so the concept is just changing the skiplet instead of the table, and the all the technique and code logic here it's similar to the hash table. So we try to run it and see what happens to see which one is faster, which one is slower. All right. Oh, that's so quick. Oh, sorry. I forget to change the name here. So int. Okay. Right. Let's try and run it. I think it would take about 20 seconds for 2 runs, I think, and it's gonna be 10 seconds for each. Let me see. I think the skiplet gonna be slower than the hash table. Yeah, it's 12 seconds. Oh, It's much slower. I think it have to be, yeah, 12 seconds for average. So in conclusion, of course, the hashable and the quicksort, it's the best solution and it's quicker than the skiplets. Thank you for listening. That is the end of my explanation about the assignment.